Every single day, you generate gigabytes of data. From your social media posts to online purchases, this vast digital footprint isn't just floating in the cloud, it's meticulously organized and stored. But have you ever stopped to wonder how billions of pieces of information from countless users worldwide are efficiently saved, retrieved, and kept safe? Understanding how databases store data isn't just for tech geeks, it's fundamental to comprehending the digital world we live in. It impacts everything from your online banking security to the speed of your favorite apps. By the end of this video, you'll have a crystal clear understanding of the intricate journey your data takes, from a simple click to its final resting place, and the ingenious systems that make it all possible. The invisible backbone. What is a database? At its core, a database is simply an organized collection of information. Think of it like a superpowered digital filing cabinet, designed to store, manage, and retrieve data quickly and reliably. From tiny personal apps to global enterprise systems, databases are the silent, invisible backbone. Every time you like a post, buy something online, or even just open an app, a database is working tirelessly behind the scenes. It's not just about storage, it's about making the data accessible, searchable, and secure, often for millions of users simultaneously. Imagine trying to find one specific customer record out of billions without a database. It would be impossible. From data to bits, the digital transformation. Before data can be stored, it must be digitized. Whether it's a photo, a word, or a number, everything gets converted into binary code, sequences of zeros and ones. This is the universal language of computers. Each 0 or 1 is called a bit, and 8 bits combine to form a byte, which can represent a single character. Once in binary, these bits need a physical home. Historically, data was stored on magnetic tapes, then floppy disks, and hard disk drives, which use spinning platters and magnetic heads. Today, solid-state drives, or SSDs, dominate with their flash memory, offering incredible speed by storing data electrically. The file system foundation, organizing the bits. Think of your computer's operating system as the ultimate librarian. It doesn't just dump all those bits onto the drive, it organizes them into files and directories, creating a hierarchical structure. This structure is managed by a file system, like NTFS for Windows or Extension 4 for Linux. Underneath files and directories are blocks, fixed-size chunks of data on the physical storage device, typically 4 kilobytes. When you save a file, the file system breaks it down into these blocks and finds available spots for them. It also creates an inode for each file, which is like a file's passport, containing metadata such as its size, permissions, and where its data blocks are located on the disk. Relational database storage, tables and indexes. Most traditional databases are relational, organizing data into tables with rows and columns. Think of a spreadsheet, but infinitely more powerful. Each row is a record, and columns define the attributes. For example, a user's table might have columns for ID, name, and email. The Database Management System, or DBMS, takes these logical tables and maps them to physical storage. So far, we've journeyed from bits to complex B-trees, but here's where it gets really interesting. How do databases ensure that even with all this complexity, your data stays perfectly consistent and never gets lost, even when systems crash? The answer lies in some clever engineering principles that are truly the unsung heroes of the digital age. Under the hood, these tables are often stored in heap files, essentially just raw collections of data pages on disk. But finding specific rows in a large heap file would be slow. This is where indexes come in. The most common type is a B-tree, a self-balancing tree data structure that allows for highly efficient searching, insertion, and deletion of data. NoSQL's flexible approach, beyond tables. With the rise of the internet and massive, unstructured datasets, traditional relational databases faced limitations. Enter NoSQL databases, designed for flexibility and massive scalability. Instead of rigid tables, NoSQL databases offer diverse storage models. Key-value stores, like Redis, simply pair a unique key with a value, perfect for caching. Document databases, like MongoDB, store data in flexible, semi-structured documents, often in JSON or BSON format. This is ideal for content management systems or user profiles where data schemas can evolve rapidly. Then there are graph databases, like Neo4j, which store data as nodes and edges, perfect for modeling relationships, like social networks or fraud detection. The magic of caching and buffering, speeding things up. Even with efficient indexes, constantly reading and writing to disk is slow. This is where memory hierarchy comes in. Your CPU is tiny, superfast caches, then there's faster but smaller RAM, and finally, slower but larger disk storage. Databases use RAM as a temporary, high-speed workspace. The database maintains a buffer pool in RAM, loading frequently accessed data pages from disk into it. When you request data, the DBMS first checks the buffer pool. If it's there, it's a cache hit and incredibly fast. If not, it's a cache miss, and the data must be fetched from disk. This intelligent caching drastically reduces disk I/O, making your applications feel snappy. Ensuring data integrity, ACID and replication. Storing data isn't enough, it must be correct and reliable. This is where the ACID properties of transactions come in: atomicity, consistency, isolation, and durability. Atomicity means a transaction is all or nothing. Consistency ensures data always moves from one valid state to another. Isolation means simultaneous transactions don't interfere with each other. And durability ensures once committed, data is permanent, even after a system crash. To guarantee durability and protect against hardware failures or disasters, databases employ replication. This involves maintaining multiple copies of the data across different servers, sometimes even in different geographic locations. If one server fails, another can instantly take over, ensuring your data is always available and safe. This is why major services rarely go down completely. Let's recap. Data is digitized into binary, stored physically on drives, and organized by file systems. Relational databases use tables and B-tree indexes for structured, efficient access. NoSQL databases offer flexible models like key-value, document, and graph for diverse data. Caching and buffer pools in RAM drastically speed up data retrieval. ACID properties and replication ensure data integrity, consistency, and disaster recovery. The key takeaways: every digital interaction relies on sophisticated database storage mechanisms. Databases employ multiple layers of abstraction, from physical bits to logical tables, to manage data efficiently. Understanding these principles highlights the immense engineering behind the seamless digital experiences we take for granted. If you found this deep dive into how databases store data valuable, hit that subscribe button and ring the notification bell so you don't miss our next tech breakdown. What's the most surprising thing you learned today? Drop a comment below.